Epidemiological modeling, a presentation for maths students. First, some trigger warnings for those university students watching. No abstract model of a person was killed, but some may have been harmed. This presentation contains differential calculus, probability distributions, and some history. Please note that most of what will be discussed is not mathematics, in which you are either right or wrong, but mathematical modeling in which you are always wrong. As the statistician George Box pointed out, the question is whether the model is useful. The Nobel Prize-winning physician Sir Ronald Ross and mathematician Hilda Hudson developed what are known as compartmental models. In these models, an individual is placed in different compartments based on the state of their health. In particular, we'll concern ourselves with SIR models. S stands for susceptible to infection, I for infected and infectious, R for recovered and immune to reinfection. The individuals move from the S compartment to the I to the R. We'll assume that there is a constant population, that there are no births or deaths, that individuals can be chopped up into pieces smaller than allowed by the laws of physics, never mind the laws of man. This allows us to differentiate the equation to produce the model. Not that that equation is of much use. We need to make more assumptions to perform what is known as a closure of the model. Assume that all individuals recover from infection over a constant time period. Because there are I individuals, we can create a model for one of the unknown terms. The equation can be rewritten in terms of the basic reproduction number and some proportion. The basic reproduction number is the number of individuals one individual will infect in an otherwise susceptible population. Hence, the infection curve is the result of a dynamic imbalance between some unspecified growth and exponential decay. Exponential growth occurs when the proportion is constant and large enough. Eventually, the number of infected will be larger than the size of the population, whilst it heads off to infinity. I call this the so bad it breaks the laws of maths model. Note that Dr. Farr showed epidemics don't grow exponentially in 1840. Those familiar with social media will know that some people just like to be contrary. One argument I've heard is that it grows exponentially, then it doesn't. However, they never seem to be able to state the time, what happens, and what the consequences are. I call this the wants it both ways model. Other people say that's not their definition of exponential growth. Even those who work for dictionaries support them. The only examples of exponential growth that I can think of are artificial. For example, compound interest dates back to the Babylonians, if not before. There are plenty of examples of exponential decay, radioactive and thermal come to mind. I call this the failed maths so badly that they can only get a job working for a dictionary model. In 1927, the blind biochemist William Kermack and the physician Anderson McKendrick produced a model which has good agreement with a number of data sets and has come to be known as the standard SIR model. The infected equation of which is the imbalance between logistic growth and exponential decay. The logistic function is merely a transform of the hyperbolic tangent and maps the infinite range to the finite. So far, I've only talked about deterministic models, those for which the future is always known. However, real life is noisy, and now I'll talk about cases where X is a random variable sampled from some probability distribution. In a lecture from the Roslin Institute in Edinburgh, I noticed the enclosed slide which gave 4 different normal distributions with the same expected value corresponding to logistic growth. The lecturer must know that at least 3 of these are not useful. In general, when looking at the literature, it appears that there are more epidemic models, both deterministic and stochastic, than there are datasets. Changing the notation of that slide to match this one has the normal distribution, where the variance matches one of those 4 models. This implies that X varies over an infinite range rather than from 0 to 1. So it appears that the authors of those models were just randomly guessing. There is a discrete model that I call the minimal SIR model. When scaled, its discrete probability distribution can be approximated by a logit normal distribution. That is, the logit of x is normally distributed, the logit being the inverse function to the logistic function. The minimal SIR model is a model so simple that you can perform a simulation with 2 packs of playing cards, such as on the first slide. Do you know how an epidemic grows? 1 infects 2, 2 infect 4 or 3, or 2 or 1 or none, all with different probabilities and a weighted average of logistic growth. Thank you for your time and goodbye.